10 years experience in academic and industrial research, and his main research interests include multimodal representation learning, causality, word models, reinforcement learning, and embodied AI. Let's welcome.
I know you guys are all tired, right? We are running out of time. And I'm feeling two things. One thing is it's great to talk in the last because some of you really tell about lots of problems, right? Language model has lots of problem, hallucination and synthetic data, use it or don't use it, right? So I'm exactly addressing these things, so super excited on that sense. But I'm scared because I'm talking some of the opposite, recommending some of the opposite things than some of you did, But it's a research, it's a good thing, right? So it will create the debate, it's okay. So all of a sudden, world model has become very popular this year, after the Sora probably. OpenAI don't admit it, but I believe that's world model. And recently, all of the big lab is releasing one after another in last 1 or 2 months, okay? So rather than presenting some of the 1 or 2 specific paper, what I'm trying to do is what is world model? Still because people don't know. I'm working in this area for 5 years, just world model 5 years. I still don't know what is world model, to be honest with you. And my friend was asking me, can you format as a mathematical? I struggled, And so I will introduce what is world model. And I'll give you some timeline, some of the good work, so you can go back and read and get grips into it, and know more, And third part, I will try to tell what are the major problem, and what are the open question problem we should solve before if we get ever AIG, if we ever reach there, Okay, so let's start it, So until now, the computer vision community was working on what is where. That was famously said by the David Marr, right? What is where. And that was the meaning of scene understanding, right? But we talk very less about action, what will happen. What will happen if I take this action? This image, just looking from this image, if your model don't have any prior, any innate prior. Innate prior means from your birth or from your experience. Or if you haven't seen the other event, you cannot tell really what will happen after you remove this image. Or what will happen if I put this big stone to the top of the, you honestly cannot tell it. I remember there was a debate, somebody saying, you can't tell. Yes, I can tell because I have seen before. I have an innate bias. Without innate bias, you cannot tell it. And the model parameters initialized from the random initialization, how the hell, how that we can know that will happen? No, impossible. For example, if you see this image, this is one of the very famous from MIT, Josh Tannenbaum group, and he's one of the pioneering in this work. He's working for many years, 2 decades. And you can try a couple of trials, and you can know, the goal is how can you put this red ball to the green ball, that's the goal, And eventually, after a couple of try, we as a human, and we can do this. Okay, how we do this, right? You have a problem, and you try to simulate in your brain, and you, rather than taking any actions, you try to think what will happen if I draw this triangle, if I draw this box to the here or there, and then finally you think this might be the best option. You try it, and then you take action. And getting that actions, you might get failed. Okay, is that okay to be failed? And then based on that, you get a feedback, and you update your belief, right? So you have to remember these things. You do the sampling, you do simulate in your brain imaginations, then you take very few actions, stick to the wall, you get a feedback, and you update your beliefs, and that's how you improve, okay? And one more very famous example, large language model. Without talking LLM, how can we, right, in any workshop. Emily found a desk and placed a cell phone on top of it, putting the line down next to the cell phone. She finally put an apple onto the desk. How many items are there? GPT-4, just 2. You know why? Because cell phone in the desk, there is a relationship, right? And there is another relationship, apple on the desk. There is a relationship. But there is no relationship of the line to the desk. We don't need any brain to tell that LLM need a world model. I'm sorry. need it. This is pretty clear, right? And I mean, we know why GPT-4 is not working here. I mean, similarly, I can go like many examples because I told you, I can go very examples, okay? So these are some of the inspiring examples why we think world model is needed, or we must know what will happen after the action you take. And there is another inspiring story from very famous book. I'm sure many of you has already read it. There is a two kind of system. One is a very fast, efficient, and you don't think much. You just take the action, system 1, and there is a system 2, which takes time to plan, slow, but it's more accurate and imaginative. And the good thing, and in a cognitive psychology and or cognitive science, we study this kind of system as a mental model, and in a AI machine learning things we call them as a world model. Probably I would call environment model. I will come to that later. It's not truly world model. Okay. So, and a good thing about this is this kind of world model. You can have both systems because we are a computer. You can design which the connections we can have from here to there, and you can design both of it. So that's a good thing about the world model. So what is the research motivations? And I believe strongly like hallucination is in a large language problem is a physical grounding problem, right? And the theory of mind, I remember some of you was mentioning like theory of mind can help us, like modeling the thought process, emotions and intentions, right? If you can model that, then only you can remove the hallucinations. Otherwise, how can you do that? Like if it's an embodied agent, we cannot. I mean, some of the medical imaging people and some other people like presenting here, like it's very hard to execute the real action in the real world. It's very expensive, and if you can generate a model which can generate the efficient data, then you can train your efficient embodied agent, right? You can try the cyber attack like kind of agent using like real things. You have to simulate those things. I give you like concrete example of why you need to be simulated. And by default you get a planning using a world model, right? So what is world model? This is the closest definition I come up. So to see is to. I work in computer vision, so I give them from the computer vision perspective, but you can simulate on other things. So like to see, to know what is where by looking. That means scene understanding. For example, object localizing. That is just see. And what is the mental model or world model means learning the physical properties of the environment. Physical scene understanding, that's what I call it. Means all of the above and learning the physical attributes, relationships and affordance of an object. And dynamic model likely past and future conditions of the agent's interaction. And that is the world model. So, because of the time, I'm not going to detail. You can see in a scene understanding, we just drew the image, but here you have a direction and magnitude of your speed, how speed you are going. So that is a kind of physical scene understanding, rather than just the semantic segmentations. And similarly, I think from the image, you're going top, you'll fall down. So because if you don't have a world model, you'll fall down. Or you should know if you cross the pedestrian, what should be happen. Otherwise, how do you know? If some person is coming from here, should you go to the pedestrian? Because you might kill more person, right? You might just, I'm sorry to say, you might just have one accident in the road. But to avoid that, you cannot go to the pedestrian crossing. If there's more people, it will have more disaster, right? You should know these things. So for that, you need a world model. Okay? So perception to action is all about the world model. So one more thing is like we think world model is about reinforcement. It's not. It's not. Like because it happened that most of the reinforcement learning people collecting the data for robotics is very hard. That's why they thought of world model and they started using it. But world model can be anything. It's a language world model. I will give you some of the examples. It can be a language model for regression problem. Some world model for the classification problem. So the world model does not necessarily mean model-based RL. No. Some people think like whenever I talk about the world model, they think it's a model-based RL. No, it's not. It can be about anything. Okay? So now I'm going to some practical aspect. In a world model learning, there is a two approach right now. One is learning the physics engine, but is a neural network is popular, so it's about neural physics engine. And the second is dynamic prediction. Dynamic prediction is very simple actually. We don't know how to do it. So that's why we need all of you, and more of us. how to do that. So right now we do very simple approach, dynamic predictions. Given a state, current state, observations, and probably the kind of action you can take. And if you can predict the future from the present and past, if you can predict the futures, that means we know the world model. That is the simplest cartoon version we use it right now. Probably that's why we need a more brain, you know. So one example of learning the neural physics engine. So represent the world state not just as an object but as a particles. You can use those particles, signals, and you can predict same dynamics formula I just said you, very simple cartoonist formula, and I can get the very pretty much from the prediction again same from the group of the same, yeah, cool. So that's the one. I don't work too much on that, so I'm not very expert of that area, but I just give you some example. But this is the area I work on, so I'm going to talk more about these directions of dynamic predictions, learning the world model for computer vision, machine learning things, and recently I moved to the language. So rather than talking about the one paper I already told you, I give you the timeline, and I give you the flavor, and what kind of problems are there, okay? So one of the earliest model, by, of course, reinforcement learning, Richard Sutton, in 1991, he presented the architecture called Dyna architecture. What does that? In reinforcement learning, you have observations, you take the actions, and you get the reward and next observations, right? And based on that, what your function is, you want to maximize the reward. So that was the one line of reinforcement learning work. So what he did is at the same time, he learned additionally the transition, the formula, given the current state and past state. He also predict the futures, the dynamic model. So now what he does is, using this dynamic model, start at random point, generate the synthetic data now, because you have a dynamic model, right? And you can randomly select the action, right? Or you can use your value functions to select which is the best actions. And you can generate synthetic data. And he merged the real world interaction and the synthetic data to train the reinforcement learning agent, and he got a better result. That was one of the earliest model in a machine learning things or AI things, which shows the world model has improved the sample efficiency and they are good. That's why one model is generative model. So the generative models are already popular before 20, Okay. So, and there's another work in a 2018 is from this famous Jorgen Schmidt-Huber, those of who know the recurrent convolution, recurrent neural network, LSTM, and he is the guy. And his group with the David Ha, they propose a model which used all the advancement of the deep learning, and he does very simple things, same simple things. He used VAE, that time very popular to learn the state abstraction. Given the image, they learn the VAE, that's called visual model, V model, and then they use the MDN RNN, is simple RNN, to predict the dynamics, and they learn the controller, not using reinforcement learning, but using the evolutionary algorithm, the genetics algorithms, and they got the state-of-the-art result. Not just that. That time, Deep RL was super hot from the DeepMind and so many other papers, right? But still, this is the first model to solve the car racing problem from the if you know the famous car from the OpenAI simulator, right? As Jan LeCun always said, RL cannot give you AGI, so do I said, look at the parameter of VAE, 4 million. Look at the parameter RNN, almost 500,000. Look at the controller parameter, less than 1,000. And it beats that time, 2018. You just believe in 2018 how famous was the deep RL, right? It's not a joke that time. And it beat, this simple model beats all of this work. And that tells you RL is, yes, sharing the peak. Because if you can perceive well, if you know what will happen, for the action selection is a almost no-brainer. So it's a cherry, yes. Right? And after this, there is a work in 2019, next year. This work systematically said, in this previous work, they just did one go, it's just engineering now after that, lots of researches. And they said, I just click the data, interaction, first layer, second layer, I learn the wall model, third layer, I learn the policy from the wall model and repeat many times. Of course, if you collect the better data from your agent's improvement, your wall model will improve, so your controller will improve. That's obvious actually. And using this technique, they got a state-of-the-art result in Atari. Again, you have to remember that time, all the deep RLOs, Q-learning was so hot. Everybody wanted to do Q-learning that time, right? And now, after that, this is another paper like Dreamer versions, like Dreamer version 2, 3. Those who works in deep, model-based RL, I'm sure all of you know. So what they did is they saw you have a 3-phase learn dynamic from the data set, V model, and then train your behavior only on the imagined data. You learn your wall model in the real data, but you train everything, your model, your agent only on the only imagined data. And it compete with anything. And it was the first model-based RL you call it, or like wall model you call it. It compete on both category, efficiency category as well as big data category. Means like training in 10 million, 100 million time steps. So in both category, it wins. Okay. And I just want to show you this because you see the learning the wall model is so simple, right? It's not complex things. So anything advancement in a deep learning is totally parallel. And there are a paper, of course, using a transformer, and they can scale it. You know, in the computer visions, there is a paper called like Mux autoencoder, which is the state-of-the-art vision model. Just if you talk about the vision model, right? MAE, and they just use the MAE technique to learn this V. You know, just if you remember 3-phase, they just use this V to learn that things, and everything else is same, right? And there are some advancement, but we all know these advancements, like rather than continuous variable, discrete variables works better in a dynamics prediction, in a video predictions, right? And these kind of all very common knowledge, you know. And he used all those kind of common knowledge and put it, and it produced the state-of-the-art results, right? And disclaimer, this is a work by just me and my friends, and what we showed is not just dynamic predictions, all of the other deep learning advancement is applicable in a wall model. You can add the contrastive learning or other regularizers to improve your wall model. So in this work, what we did is very simple. If you just, and this is right now state of the art, if you know they like Curl, RAD from all like DeepMind, like Berkeley, this all big groups, and they are very good on 60%. They got 70% on in distribution. But when I test on out of distributions, out of domain, like or this kind of distribution data, and they just failed 5%. There's a lots of work to do. And then if you train the invariant features using the contrastive learning and some other technique, then you can improve. And surprisingly, very surprisingly, I know some of the presenters were mentioning grounding dyno. And this is the grounding dyno accuracy is 40% with the just 100K data. So you have a grounding dyno, you use the B model, you state extracted as a grounding dyno, and everything else is same, right? That's a perception model. And that has been trained on millions and millions of data and many days in a computer. And the Recur model, which we propose, is just trained on 2 days. Just 2 days, right? And from the scratch, from the random initializers. And it can beat the grounding dyno. And this is a CVPR this year. So wall model works, right? So, okay. So this is I talk about the single modality, right? And what about the multimodality, right? We all know, like I think we all agree that learned features are better than hand-designed features. We all agree, right? Now I'm sorry to say these things. Language is a human design features and tool for communications. How it can be better than learning from the original sensor or original observations? Yes. If you agree the first line, you have to agree the second line, right? I'm sorry, you have to, right? So the learning the world model from raw observations should be better. I'm not saying RGB, I'm saying example is RGB because RGB probably captures them much better or than some of our earlier presenters. So RGB cannot capture everything, right? You need a thermal. I agree on that. But the point here is learning from the full observations is better. It has been proven. Because when the people design the language, we have some explicit annotations. We don't care about the so many implicit things. We care about what is important for us. That's how we design the language, right? What is important to communicate for us. So that's really pitch for the multimodality, right? Means prior accelerate the learning, structure prior, language prior, all other prior. And because when we talk about the multimodal, for some logistic reasons, maybe all the data are not available as much as we wish, so the language and vision are two modality, candidate modality, right? So language is good for discrete design. They are discrete by design. Abstract and global context is better represented in language. But explicit representation of what we believe is important. So means implicit information is missing in language. But in a vision is a continuous by nature, which is good. Precision, better for local detail, right? You cannot describe the whole this wall very well, right? But the image can tell you the very detail, very well. That easily pitch the multimodality. That means they can complement each other. So there is no doubt these two should be the future. The multimodality should be the future. Okay? So when we talk about the multimodal again language, right, there is a two kind of model, right? One is the early fusion, one is a late fusion. Like some late fusion is like cliff kind of model. So I'm not going to talk too much like, the cliff kind of model, you learn the different modality and you at the end you learn, and there's early fusions like dino kind of modality where you can fuse very early. Right? And there is another very famous thing just now, I told you this like last month, the genie from DeepMind, this foundation world model. And they train on internet data. You see, they train on something that can easily change on other things. Means you can like easily redirect to any other things. Okay? And the language, because I know there's a lots of language. How the pre-trained model, right? Because we cannot train the big language model ourselves. So how can you use this power of language to convert it to the world model? So that is the idea. So you can have a language as a backend, LLM as a backend, and then you have a world model. You can think of a chain of thought kind of agent, right? An agent who can ask like chain of thought kind of questions. And you have a belief, you have a goal, and you can multiple times you can ask to your LLM. And you can easily, using a very, very thin wrapper, you can easily convert to the LLM back into the world model. So you don't need to train from scratch. That's the point. Means you can have an efficient technique to convert the existing technique to the world model. And if you change that back in from LLM to the GPT-4V, then it is a multimodal world model. Right? Okay. So I remember some of the from the audience and the presenter was saying grounding is a big problem, and this is again work by us, my group and myself involved. So we propose how can we do the better grounding for the world model. So what we did is rather than masking a scene randomly, we mask the object in the scene. We mask the object and give the text prompt. So there was a monitor. You mask the monitor and say there was a monitor. And you do the early fusion. And this way you can force the grounding. I'm not saying that ChatGPT-4 kind of model trained on a billions of data, given an image, given a like a description, it can be ground. But you need millions of data. You have to find the unique corner cases. But in this technique, we believe you can like do the grounding which are very, very efficiently, because you can telling what is what, right? And using this, surprisingly, we got again a better result than other. Auto distribution, don't bother by this result. This all model in distribution gets 60-70%. State of the art, no problem. This all listed model are state of the art right now. But if you test on out of distribution generalizations, they all fall down to the 5 from 60, 70, 80, right? So still the Max-Waller model is not great. Probably it needed to be new technique, but it's still slightly better than them. And you have to remember they are only trained on 100K images as well. Okay, so I'm grossing very fast because I'm asked to finish on 30 minutes. So hope you understand why I'm running very fast. And the most interesting, when I was a PhD student, I always look for what is the hard question, what is the important question to work on, and I wish I knew all those things before then, So these are the hard questions, we should be asked, Auto-regression. You see the world model is training by auto-regression, yeah? Because you predict the time t plus 1 given the time t. ChatGPT, all GPT model, all, but everything is almost all is trained by auto-regression. Now the question, we as a student, we should not be just using, we should be asking the question, is predicting the next token only sufficient or not? Like, I know some of the famous people, Ilya or Geoff, they said probably the future prediction is just doing the compression, because we all, AI scientists from last 50 years, doing the compression, right? We believe that learning this is the compression. So probably they're doing already the compressions, because if you can predict what will happen, that means you know that your compression, you have a knowledge of compressed knowledge, this is enough. But you know the BERT model, right? Which I am sure some of you still use it. I know it is not state of the art, but remember that time it was the state of the art. It was beat the GPT first person, right? And it has a more additional loss. Then why don't we believe adding this kind of additional prior will still beat the current state of the art? The problem is data is skill, right? They train on the multi-billion data. You cannot train, and we don't know if the data is working or nice algorithm is working. That's the problem. That's the problem we all facing right now. Data is working, good quality of data, winning, compute winning, or idea or algorithm winning. We don't know. I think we as a community will figure it out how to separate these two things. And the second thing is, almost all of the work, they do the image prediction. When they call the world model, they give the current image, they predict the future image. So now the question is, do we need to predict the individual object in the scene as separately? Do we need to learn the dynamics of the object separately in the world model? So that's one of the very important questions. Mostly we don't, but I believe we should actually eventually. And how can we do? We have the very fast object detections, and we have a graph neural network. Probably we should be, some of you should write a very awesome paper using a graph neural network learning the world model. Another thing is causal world model. Do we need a causal world model? Or, because in a reinforcement learning or action selection, agent is already interacting, right? You take the action which will maximize the reward. Isn't that a causality in a sense? Because you know what will maximize your reward. You select the action based on your observations, which will maximize the whole reward. Is the RL is already doing causality? Or interactive learning is already doing the causality? Or, since in a world model we already learning the next observation given the current observation given the current observation and current action, does that mean the causality is already there? Intervention, because action is intervention. Those of you know the causality is the intervention. You can think action as an intervention. Since action is already doing the intervention, does this kind of modality and world model is already learning the causality? Or we need to learn, okay? Another thing is data-driven approach. Is the data-driven approach is good enough to learn the world model from the observation only? Or we need to learn the physics, or how close we need to go. Level of abstractions. How much level of abstraction do we need? How much high level planning do we need? Pixels, line, parts, objects, groups, these kind of things, or character word. What is the level? In a world model we go the next, or how many iterations we need to go? How many level of abstraction? But that's the problem with the deep learning right now, right? Every answer goes through the every weight. That's wrong, right? Some problems are complex. We need to think more, maybe compute more. Some problems are easy. We don't need a 10 billion, right? Maybe expert of things, right? Or maybe not slightly different architectures do we need, or how much, these kind of things. And obvious questions: single model for all tasks or task specific? Will the dinosaur survive? We should ask this question. Okay. So having said that, I think I correctly finished in 30 minutes. World model, learning the internal mechanism of the environment. Why I said environment is, world means huge data, right? Your model only know the data you gave. That's your environment. I think we should better call right now the environment model, and hopefully in the world model we'll figure out how to learn that. And that means world model is a generative model. World model is data efficient. World model generalizes to downstream tasks, can use for planning, grounded to the environment, so help to minimize hallucination. And I think multimodal is the future. Hopefully, I believe multimodal causal world model probably will specific wrapper or distillations, and to get the world model, which I give you the one example. Thank you.
Questions? Yes.
It's quite interesting to think what people do inside our heads, where we have networks of biological neurons. To what extent you can identify symbolic representations of the world that we use, or to what extent it's just implicit. So we've got questions to answer in neuroscience which are similar, in parallel.
Oh, okay. Yeah. Thanks. Yeah, I'm from cognitive science background. So I did my MS in cognitive science, so that's how I moved to machine learning, and thanks. Yeah, that's it.
So yeah, it would be interesting because in Sora, as far as I know, there was no explicit modeling to let the model learn like physics behavior.
Yeah.
So right, it emerges from the vast amount of data, I guess.
Sure.
So would that make sense to have an explicit, like specific loss functions and whatever to explicitly enforce the prediction of the next time steps basically?
If I understand your questions correctly, to explicitly forcing works better. If I understand your questions, and the second is like, sorry, that's the question, right?
Do you have any ideas, or is there any work explicitly tries to model the predictions and the physical behavior? In Sora, it emerges automatically from the vast amount of data, right?
Sorry, so what do you mean that physics means next is predictions? They don't know the physics. We believe implicitly the dynamics model will learn it, but there is no explicit learning mechanism.
But could we have the idea to, because we know we have some idea of our own physics, right? Our own world's physics. So could it make sense to enforce?
Yeah. Of course, prior works. So like the paper I said, that's our paper, which is there right now. We even like the simple prior works. Even forget about the physics. Like if we just forced to predict the depth as well, just with the next observation is improved. Like other alignment things works. Yeah. Yes. Any kind of prior you inject in the world model, they does better. But to answer your very best answer, like how much physics, I don't know. We don't know. People trying, like some of the people I know, they're trying to learn the physics engine and trying to call open domain kind of problem, but
Further question? Okay, let's thank Dr. Rujo Podell. Now comes to the last keynote speakers, Ashkan Kaza. Ashkan Kaza is a postdoc researcher at the University of Oxford at Tours Vision Group, and his research focuses on the AI safety, primarily on interpreting neural networks in the context of multimodal